Hello my dear students, welcome back to my channel Chemistry with ASR. So in today's session, we are going to learn about the features of pi bonds. Before that, let us look at the structures of the molecules. What are pi bonds? What are sigma bonds? Okay, so firstly, let us understand how the molecules are formed. Okay, so you know that the entire study of the carbon and its compound is organic chemistry, and rest of study of rest of the elements in the periodic table is inorganic chemistry. So first let us understand carbon, okay. So what is the electronic configuration of carbon? It is 1s2, 2s2, 2p2. So that is 2, 4. Okay, so there are 4 electrons in the valence shell. How many electrons? There are 4 electrons in the valence shell. It needs 4 more electrons to complete octet. It needs 4 more electrons to complete its octet. Energetically, if we see, it is very difficult for carbon atom, okay, to gain 4 electrons or to lose the 4 electrons. So energetically, it's very difficult to gain or lose 4 electrons, right? So therefore, carbon will always combine with atoms by mutual sharing of electron and thus forms covalent bonds. What does it form? It forms covalent bonds by mutual sharing. By mutual sharing. So much is clear? So this carbon is always tetravalent and it forms 4 covalent bonds. It forms 4 covalent bonds. You can see it in the structure. You can see that the carbon can always form 4 covalent bonds. So that's why it is tetrahedral in its structure also. It is tetravalent. If I consider an example of methane, this methane, the central atom is carbon. You have the hydrogens at the corner of the tetrahedron. Okay. So it has formed 4 covalent bonds. 1, 2, 3, 4. All these 4 bonds are called sigma bonds. What are they? Sigma bonds. So this carbon is sp3 hybridized. sp3 hybridized. Carbon is sp3 hybridized. In yesterday's session, we were looking into the sp3 hybridization, sp2, sp, isn't it? So today let us look at what are these sp3, sp2 and sp hybridization. So when all the carbon atoms are sp3 hybridized and each sp3 hybridized orbital will direct itself to the corners of the tetrahedron, to the four corners of the tetrahedron, forming tetrahedral geometry, and it binds with the hydrogen atom. This you already learned in the bonding, chemical bonding lesson, but still just you need to be thorough with your basics. Therefore, I'm teaching you again. So this overlap between the p orbital, sp3 hybridized p orbital, and the s orbital of the hydrogen atom. What is this? We have written hydrogen atoms at the four corners of the tetrahedron. So hydrogen, what is the electronic configuration of hydrogen? It is 1s1. So each hydrogen atom has one electron in its valence shell. Now, I said this carbon cannot either lose the electrons or gain the electrons. So therefore, it can mutually share and form covalent bonds. How many covalent bonds? 4. And these bonds are sigma bonds. What are they? Sigma bonds. This is hydrogen. And this is p orbital, hybridized orbital, sp3 hybridized orbital of the carbon. Okay, so it forms a tetrahedral geometry like that. I hope this is clear. Now what is a bond angle? It is 109, 28 minutes. 109 degree, 28 minutes. And the hybridization of the carbon, it is sp3 hybridized. I already told you, right? So this was clearly studied by Van 't Hoff. So therefore he was awarded with Nobel Prize in the field of chemistry in 1901. Why? Because he laid the foundation of the stereochemistry. He was also known as the father of organic chemistry, because stereochemistry, the geometry of the molecules, is very important. If we understand the molecular structure of the organic compounds, it is very easy for us to predict the properties of the organic molecules. Is that clear? So this is the shape of the molecule, and here you need to observe that all the bonds are sigma bonds, and this molecule methane, whenever in a molecule if all the covalent bonds are single bonds, then I call the compound as saturated. I call the compound as saturated, and the bonds are sp3 hybridized. I'll take one more example for you. Now C, single bond C. There are 3 hydrogen atoms. I told you it is tetravalent. That means carbon can form maximum of 4 bonds, not more than that. Right? So you can see that how many types of bonds are there here. 1 carbon-carbon sigma bond. Right? And 1, 2, 3, 4, 5, 6. 6 carbon hydrogen sigma bonds. So what is the name of this molecule? It is ethane. And it is a saturated hydrocarbon. So much is clear? Okay. In the first molecule, you already know that how many sigma bonds are there? 4 carbon hydrogen sigma bonds. Alright. Next we will look into the unsaturated hydrocarbons. Unsaturated hydrocarbon. For example, we have let us look at ethene. Ethene, the structure is C double bond C with two hydrogen atoms attached to each carbon atom. Now, this each carbon atom is sp2 hybridized. Both the carbon atoms are sp2 hybridized. Okay. Now, when we look at the bonds, there are 1, 2, 3, 4 carbon hydrogen sigma bonds, and you can see that 2 bonds are there. This is an unsaturated hydrocarbon with carbon-carbon double bond. And if you consider the alkyne, it has got carbon-carbon triple bond. So both of them come under the category of unsaturated hydrocarbons. Now here there are 4 sigma bonds and 1 carbon-carbon sigma bond and 1 carbon-carbon pi bond. Now what are these pi bonds? These pi bonds are nothing but they are formed by sideways overlap of the orbitals. Okay. So you can see in the structure, carbon, 2 carbon atoms are there, and these orbitals, whatever the green structure you are able to see, these are the 3 sp2 hybridized orbitals. They orient themselves along the geometry of trigonal planar. Okay, so you can see that all the carbon atoms and all the hydrogen atoms, they are orienting themselves in the corners of the trigonal planar geometry like this. It is something like this. Carbon, and the bond angle is 120 degree. Bond angle is 120 degree. Okay. Now let us see some of the features of these pi bonds. What are the features of the pi bonds? See, here they are forming by the sideways overlap. The orbitals are overlapping in the sideways. Say for example, this is the hybridized orbital. Okay, and you see that there is sigma bond, that is the overlap between the s orbital of hydrogen, here s orbital of the hydrogen, and you have s orbital of the hydrogen. Now one unhybridized orbital, p orbital, will overlap to form a sigma bond. But this is in an ethane molecule. But I wanted for the uh, ethene molecule to show the pi orbitals. So what I will do, I will just remove one of the hydrogen and show you that how the orbitals are overlapping. So you need to understand this concept slowly. Only then it is going to help you in future. Meaning to say, the entire second PUC one part of your book, you are going to learn only about the what? About the organic chemistry. So there are many compounds. So therefore, you need to understand that here 3 sigma bonds are formed by sp2 hybridized orbitals. Correct? Now here you can see one sigma bond is here and one sigma bond is here with hydrogen. Now I need to show the pi bond. So these are unhybridized orbital, and how are they overlapping? Sidewise, parallel overlap. So this overlap has formed a pi bond. Now the rotation across carbon-carbon double bond is restricted. When it comes to sigma bond, it can easily rotate, but when there are pi bonds, the rotation is restricted. Since the electron clouds, you observe the diagram. So what can you see here? The electron clouds are above the plane and below the plane. Since the electron clouds are above and below the plane, the electron clouds are above and below the plane, the pi bond lies above and below the plane of the bonding atoms. So therefore these pi electrons are easily available to the attacking reagent. Easily available to the attacking reagent. Therefore, the pi bonds are most reactive sites in the molecules containing multiple bonds. Therefore, pi bonds are most reactive sites where in the molecules which contain double bonds or triple bonds. Okay. Now let us look into the next example, that is ethyne. What is it? Ethyne. So you know that it has carbon-carbon triple bond. It has got carbon-carbon triple bond in its molecule. So how many sigma bonds are there? 2 carbon hydrogen sigma bonds, 1 carbon carbon sigma bond, 2 carbon carbon pi bonds. Clear? So here the sigma bonds are very strong. Carbon carbon sigma bond is very strong bond, whereas the 2 carbon carbon pi bonds are weak. Clear? Similarly, in case of alkenes, there are 4 carbon hydrogen sigma bonds, 1 carbon carbon sigma bond and 1 carbon carbon pi bond. So this sigma bond is strong, whereas the pi bond is weak. This is strong and the pi bond is weak. Meaning to say, since the electron clouds are available above and below the planes of the carbon-carbon atom, it is easily available for the attacking reagent. The pi electrons are easily available for the attacking reagents. Okay. So once again I repeat, these are sigma bonds and these are pi bonds. Alright. Now there is a question for you. Pause the video. Try to answer. How many sigma and pi bonds are present in each of the following molecules? So you have C, triple bond C connected to hydrogen, double bond CH connected to CH3. Answer this molecule and write your answers in the comment section. Alright. Now I hope you all tried it by yourself. Now let us understand. How many sigma bonds are there? Totally there are 10 sigma bonds, including carbon hydrogen and carbon carbon. Next, there are 3 pi bonds. Okay, 2 of them in the triple bond and 1 in the double bond. Understood, children? I'll give you one more example. Did you get your answers correct? Yes, very good. Now there is another molecule for you. Try this and post your answers in the comment section below. Okay, so this is the question. You have to write your answers in the comment section below. Next, we shall understand the structural representation of the organic compound. representation of organic compounds. There are different ways. So first one, Lewis dot structure, but this is time consuming. Therefore, it is further simplified by writing each pair of electrons. So you are going to write dot, isn't it? You're going to represent the dots around the central atom and write the structure in the Lewis dot structure. So therefore, it is simplified by writing each pair of electrons which makes the covalent bond, that is single, double or triple, and show the lone pair of electrons on the heteroatom. Okay, so this is called as complete structural formula. Complete structural formula. For example, I have ethane. I'm going to show all the atoms in the given molecule and the bonds. This is the complete formula. Suppose there is an heteroatom in the molecule. Then I will show the heteroatom and the bond. This is alcohol. Along with that, I may or may not show the lone pairs. Okay, so this is complete structural formula. Next one. Further, this complete structural formula is simplified into condensed formula. What is it? Condensed structural formula. So here what we do, we'll omit all or some of the dashes that represents the covalent bond. So the same molecule is written as CH3, CH3. Okay, and this molecule is written as CH3OH or CH3OH. Can some or all the dashes, the covalent bonds are omitted. So this is called as condensed structural formula. Next one, it is called as bond line structural formula. Bond line structural formula. Here only carbon-carbon bonds are shown in the form of lines, and these lines are drawn in the form of zigzag fashion. Okay, we always need not show the carbon atoms and hydrogen atoms. Only if double bonds are there, we will represent it. If heteroatoms are there, we will represent it. Say for example, CH3, CH3. It is just two dots like this. It is connected. Each dot will represent carbon atom and each terminal end represents CH3. Similarly, OH. This is carbon atom with 3 hydrogen atoms. We will, to understand it better, we'll take one more example. Now here you can see that this is the terminal ends. These terminal ends are nothing but CH3. CH3. These terminal ends are always CH3. And each corner is CH2. Alright. Suppose there is a double bond or triple bond. Then I will write it as triple bond. Suppose there is a double bond here. So here it is not CH2, it is CH. This is what? CH. Terminal ends are CH3. This is also CH. This is CH2. Here only C. Here only CH. So let me write the complete structure for this for your understanding. C, CH3, CH, double bond, CH, single bond, CH2, single bond, C, triple bond, C, H, single bond. Understood? Later fill all the hydrogens. Clear? This is written in the form of zigzag fashion. Alright children. Next one. There is a next type of formula, representation of the formula. It's called as polygon formula. What is it called as? Polygon formula. Polygon formula. So many compounds in which carbon atoms are not joined in a straight chain, but they can be in the form of a rings. Such compounds are called as cyclic compounds, and they are usually represented by the polygons without showing any carbon or hydrogen. In such cases, say for example, I have cyclopropane. That means you have CH2, CH2, CH2. So each corner has got CH2. Next you have cyclobutane. Cyclobutane. Next you have cyclopentane. Then you have cyclohexane. You're showing only the bonds, not even the carbon, not even the hydrogens. Next you have chlorocyclohexane. Only the skeletal structure you are showing. Then you have OH group. So it is cyclohexanol. Okay, cyclohexanol. So these are the examples. Now, just quickly try to solve it. You have an example. C triple bond N C H O H C triple bond N. So you need to write the condensed formula and bond line formula for this molecule, for this compound. So write down. Now cross check. The condensed formula is OH, CH, Cn twice. Then the bond line structural formula is this is the bond line structural formula. Alright children, so we are done with the topic called structural representation of organic compounds. So let us meet in the next live stream. Thank you for watching.